Okay, here we go. We're starting. Here's the sort of thing we're going to learn today. Suppose I'm an ice skater and I have my arms out and my leg out and I'm spinning around like this, okay? And let's say I want to spin faster. What do I do? Yeah, well, I don't put my arms down. Where do I put my, I don't put them like that. Come on, I'm an ice skater. What do I do? Yeah, put them to my chest, right? And I put my leg in, right? So that when I'm spinning like this, then I put them in and I'll spin faster. Well, we're going to learn why that happens. We're going to learn about angular momentum and the conservation of angular momentum. And it will be fun. It will be big, fat fun. So here we go. I want to remind you that we've got linear momentum. And linear momentum says P equals mv. And remember, linear momentum is a vector, because v is a vector. Alrighty. Well, now we're going to deal with angular momentum. And angular momentum, instead of mass, we're going to use a rotational mass or rotational inertia or moment of inertia. Instead of velocity, we're going to use angular velocity. And then finally, keeping with the example of momentum where they chose a letter completely unrelated to momentum to call momentum, we do the same thing with angular momentum and we call it by the letter L. What? So there it is, L equals I omega. That's angular momentum. Instead of mass times velocity, it's rotational mass times angular velocity. But I want you to notice that angular momentum is a vector as well. So I need to take a time out now and talk about the vector nature of omega. I need to make sure you understand what direction that vector points. Imagine I have a disk, and I've got a disk that's rotating counterclockwise if you're looking down on the disk. And I wanted to know, what's the direction of the omega vector? Well, I can't say it's the same as the direction of the linear velocity, because the linear velocity has a different direction depending on where you are on the disk. If I'm here, the linear velocity is that way. If I'm there, the linear velocity is that way. If I'm there, the linear velocity is that way. You see what I mean? So I can't look at linear velocity to get a vector for the direction of the rotation of the disk. So here's what I do. I choose that vector to be perpendicular to the plane of rotation. So the first thing you should know is your vector for omega is always perpendicular to the plane of rotation. And then number two, you're going to use the right-hand rule to determine the direction of the omega vector. Here's what you do. First, you got your right hand, and then you curl your fingers in the direction of rotation, and your thumb points in the direction of omega. So in this case, my omega vector points upward because my fingers curl in the direction of rotation and my thumb points in the direction of omega using your right hand. Don't use your left hand or you'll be opposite. And since that's the direction of the angular velocity, that's also going to be the direction of the angular momentum. So hey, let me give you a problem to do. I now have a disk that's oriented vertically like this. And this disk is rotating clockwise if I'm looking at it from the left. Let me ask you this first question. Omega, since omega always has to be perpendicular to the plane of rotation, is the omega for this guy going to be vertical, horizontal, or coming in and out of the board? What's my omega going to be for this disk? Is it going to be vertical, horizontal, or coming in and out of the board? And I've tried to make it so that this disk is like rotating like this, but I had to draw a 3D perspective. Okay, how many people say omega is going to be a vertical vector just like this guy? How many people say omega is going to be a horizontal vector? Okay, so you get what I was trying to do. How many people say omega is going to be in or out of the board? Well, good. I'm glad because it's not. I tried to draw it so that your omega is going to be horizontal. So now here's the next thing I need you to do. do right-hand rule and determine, is my omega to the left or to the right? Please do that now. Which direction is omega? Please take that hand. I want to see your hand. Take that hand, curl it in the direction of rotation of the disk, and your thumb is going to be pointing in the direction of omega. Right? Okay, well, I'm hoping you guys are getting this, that this disk is rotating clockwise, and so I'm going to have my fingers curl in the direction of that clockwise rotation, and my thumb will point in the direction of omega. How many people in this class realize that in this case your omega is going to be to the right? Well, if you did, you win. Thank you very much. And so thus, because omega is to the right, that means your angular momentum is also going to be to the right. And this is a vector equation. Alrighty. So, hey, first things first, let's go ahead and have you guys do a problem where you get to plug in. Okay? Here, let me think. Here's example number 1. I have a 2.5 kilogram disk of radius 0.45 meters, rotating at 20 RPM. Find the angular momentum. Well, obviously we're going to start off with angular momentum equals I omega. Tell me, does anyone remember what the formula for the rotational inertia of a disk is? We saw it yesterday. Good for you guys, yeah. So please use that. The fact that the rotational inertia of a disk is given by the formula 1/2 mr squared. Make sure you plug that in for I. And then omega, I think you're going to find more often than not that when we deal with torque, angular momentum, rotational kinetic energy, you're just better off converting everything into radians per second. So go ahead and convert that guy to radians per second as well. So you're going to have to plug in to find I, and you're going to have to convert that guy to radians per second. Please do this now. I'm going to start writing stuff down. So what are you guys getting for this? Huh. So what'd you guys get? Anyone get 0.53? Yay. Fatima and Zina got it. Yay. Brianna got it. So it must be correct. Is there any question on any of this stuff? That's your angular momentum. Here's my next question. What's the units of angular momentum? Here the minutes cancel. Here the revolutions cancel. So what's the units? Again, radians are unitless, so I don't have to include those. So we can get rid of the radians. So kilogram, go ahead, Izina. Meter squared. Yeah, great. That's the units. Kilogram meter squared per second. That's the units of angular momentum. Excellent. And I certainly don't require you to memorize those units, oh my gosh, but you're going to have to be able to find them. For example, I know what the units of momentum are because mass is kilograms and velocity is meters per second. So that tells me that the momentum of the units of momentum is kilogram meters per second. Well, the same thing here. I know that the units of rotational inertia are kilogram meters squared, and I know that the units of omega is radians per second, or 1 over seconds, because radians have no units. So I got kilogram meters squared per second. So make sure you give proper units when you do angular momentum. Can I ask you one more question? Why don't I put the radius there? Why didn't I multiply by 0.45? Under what circumstances would I put a 0.45 there? Why is it just 2 pi, not 2 pi r? Yes?
We're finding angular momentum, not linear momentum.
Good. You're finding angular momentum, not linear momentum, right? Beautiful. Which means, because if I wanted to put a m, 0.45, that's meters. I would be finding velocity. I'd be finding meters per second, but I don't want meters per second. I want radians per second. So it's just 2 pi radians per revolution. So resist the temptation to put 2 pi r there. You're converting to radians, and that's just 2 pi radians per revolution. Don't put the r there. Okay. Hey, before I go on, any questions or issues on this? Alrighty, then let's talk next about conservation of angular momentum. And I'm going to refer first to conservation of linear momentum. Do you remember what has to be true about a system in order for the linear momentum to be conserved? Anyone?
Must be isolated?
Beautiful, must be isolated. And does anyone remember, what does it mean for a system to be isolated? What's that?
The total forces sum up to 0.
Okay, which kind of forces?
External.
Good, external forces. The sum of the external forces has to be 0, because the internal forces are already 0. So what you said was fine. Okay, but I just want you to know that for an isolated system, this is in linear land, for an isolated system, initial momentum equals final momentum. And that is for the sum of the external forces to be equal to 0. That's an isolated system. Then I get initial momentum equals final momentum. Well, now let's turn our camera over here and do conservation of angular momentum. Conservation of angular momentum. If the sum of the external forces have to be 0 for conservation of linear momentum, what do you suppose has to be true for angular momentum to be conserved? The sum of the external. What's that? Rhymes with the name of the guy sitting next to you. No.
Final?
No. Anyone thinking torque? Never mind. See, because the guy sitting next to you, please, Sahara, would you like to explain it to everyone?
Torque rhymes with door.
Thank you very much. Thank you. Yeah. Okay. Okay, so there you go. So I want you to see that if the sum of the external torques, is equal to 0, then we get to say the initial angular momentum equals the final angular momentum. And there's a lot of scenarios where there's no external torque happening, and so you get to have that conservation. Here, let's talk first about the old ice skater problem, okay? Here's example number 1, and this is actually like problem number 56 of tonight's homework. Here comes example number 1, and let me get my sheet here. Okay. We've got an ice skater whose initial rotational inertia is 6.0 kilogram meters squared, and whose initial angular velocity is, let me see, let's say it's 3.0 radians per second. Okay. She brings in her arms and her leg, and now her final rotational inertia is 4.0 kilogram meters squared. Find her final angular velocity. And I'm going to tell you right now, please start off with this. There's no external torques happening on her. No one is next to her making her spin faster or slower. All she's doing is changing her rotational inertia. Please plug in and get the answer now.
That's how you do a fouette.
I do a what?
Fouette. It's a dance term to, like, you bring your arms in and you spin even faster.
Oh, wow. Cool. I did this with my son once. We were at some Staples or Office Depot, and there was one chair that was spinning really easily, so I put him in the chair and had him go like that and like that. It spun real fast. It was very fun.
It works on there, too.
Okay. Is everyone starting with this sort of thing? The initial angular momentum is going to equal the final angular momentum? Hey, are you guys done yet? Okay, here we go. How many people got the answer 2 radians per second? Okay, how many people got the answer 4.5? Good. Why couldn't 2 possibly be the right answer? Why couldn't 2 be correct? I mean, look at the ratio, 6 to 3, 4 to 2. Why couldn't 2 be correct? Looking at this formula.
Well, you have to multiply the momentum together, and you get 18, and you have to divide by 4, and you get 4.5.
Good. Or let me put it another way. If she reduced her rotational inertia, what has to happen to her angular velocity? Say again, what?
It didn't have to increase.
Yeah, it'd have to increase. I just want you to see what we had was this situation. We had big initial inertia and a small initial angular velocity, and then much smaller rotational inertia, and so much bigger angular velocity. So you know her angular velocity is going to have to go up, right? And it's just as you guys described. I've got 6 kilogram meters squared times 3 radians per second has to equal 4 kilogram meters squared times omega f. So I got 18 divided by 4, and I get 4.5. And the kilogram meters squared cancel, and I get that. Okay. You guys okay with that? Here, I need someone who'd like to come up here and demonstrate this.
Christopher Anisi.
Imani, come on up.
Are you gonna spin me?
Yes, I am. I'm going to spin you right round, baby, right round. Oh, wait. Here we go. Put this in one hand, put this in the other hand. Okay, you're going to hold your arms out all the way. Yay. And now I'm going to spin her a little bit. And now go ahead and put them to your chest. Do you guys notice that she's spinning faster? And then put them out. And now she's spinning slower. And then put them in. She's spinning faster. Okay, great. Good. Now stay like that. Now I'm going to put 2 kilograms in each one of her hands. So let's see if you can fit them both, you think? You got good sized hands. Okay, put them out all the way. Okay, and now I'm going to rotate her. And now go ahead and put them in. Do you see what a big difference it makes? Now put them out. Yeah. Yeah, see? I love it. This is great. Okay, put them out. And now let's go ahead and stop you. And here, I'll take these off of you. Take these. Excellent. And can you get off without falling? Good. Give Imani a hand. Yay. So I want you to see, when she was bringing those masses in, what was she doing to her rotational inertia? Yeah, decreasing it. And by decreasing, was she changing her mass? No, not changing her mass at all, but she was changing how her mass was distributed. She reduced her rotational inertia, and by so doing, she increased her omega. Here, let me give you another example of that. Here comes the sun. Okay, here's the sun, and I've got a planet orbiting the sun. Okay. We already learned about Kepler's first law of planetary motion, that planetary orbits are always elliptical, and that the sun occupies one of the foci of the ellipse. We learned the second law, and tell me, what's the difference between the planet's motion here when it's far from the sun and the planet's motion here when it's near to the sun? Or is it going faster? What's that? When is the sun going fastest? Say, raise a hand. Yeah, Alejandro? Yeah, when it's near the sun. I showed you that thing on the computer that is kind of going like this. Like that. Okay? And so now, here's my question. Is this a conservation of momentum situation here? Are there any external torques acting on the sun-planet system? No, unless God is somehow pushing the planet or stopping it or something. No, there's no external torques. So this is a conservation of angular momentum situation. So now I want to ask you this. Where does my planet-sun system, where does the planet-sun system have more rotational inertia? When the planet is here or when the planet is there? Where is there more rotational inertia in the planet-sun system? When the planet's there or when the planet's there? What do you say, John? Okay, you say that it has more rotational inertia here. Okay, great. Does anyone agree with them that I've got more rotational inertia when the planet is close to the sun? Okay, does anyone think that this is more rotational inertia? Okay, Sean, why do you say this? Okay, because it's further away. How many people agree with Sean and Jonathan? Okay, hey, let me give you this hammer, okay? Tell me, if I want this situation, where should I hold my hammer? Yeah, near the head, right? Because the mass is really close. Okay, if I want this scenario, where do I hold the hammer? Yeah, at the handle. So where is there more rotational inertia? Like this or like that? Yeah, like that. When the mass is far from the point of rotation, because this is just a two-body system rotating about the sun. When you're far from the sun, it's like the hammerhead being far from the point of rotation. That's big I, big rotational inertia. Okay, so here the rotational inertia is big, here the rotational inertia is small, but they have to have the same angular momentum because there's no external torques. So where is the omega going to be bigger, here or there?
Here.
Yeah, here, right? I'm going to have the big omega here. I'm going to have the little omega there. So I want you to see that conservation of angular momentum explains Johann Kepler's second law that essentially says, I mean, it says it in a different way, but essentially says planets go faster when they're close to the sun and slower when they're far away. And that's entirely described by conservation of angular momentum. Okay, hey, there's two more examples we've got to do together. And here they come. Here comes an example that this is like problem number 58 on tonight's homework. It's example number 2. Okay, I've got a 140 kilogram meter squared carousel of radius 1.8 meters rotating at 2.0, now let's say at 4.0 radians per second. So it's going around pretty fast. A 55 kilogram boy steps onto the edge find the final angular velocity. Let me make a drawing to show you what's going on. I've got a carousel rotating at 4 radians per second, and I've got some dude who's at rest. And then he steps on, and now I've got this carousel continuing to rotate, but now the dude who's like a point mass is rotating with the carousel. If my system is the guy in the carousel, if that's my system, when he stepped on, are there any external torques happening? No, there's no second guy making the carousel go faster or slower or pushing on that guy. And so I get to do conservation of angular momentum. Tell me, who's contributing to the angular momentum of the system initially? How many people think just the carousel? Yeah, the dude's at rest. He's making no contribution to the angular momentum of the system. But after he steps on, now, do you see that the rotational inertia of the system is just increased? Because he stepped on. And so because you increase the rotational inertia of the system, what's going to happen to the angular velocity of the system? Say again? Yeah, would you say that again?
Decrease.
Yeah, think about it, it's decrease. It's going to decrease. So I'd like everyone to please do this problem. And I want to tell you, the moment of inertia of the man, you're going to have to use the formula for the moment of inertia of a point mass, which is mr squared. And I do want to remind you, I guess I'll put it out here, what the moment of inertia of a point mass is. If I've got a point mass of mass m going around in a circle of radius r, like a heavy ball at the end of a massless string, then the rotational inertia of a point mass ends up being mr squared, and it's no different than if it's a hoop. A hoop is the same as a point mass, because all a hoop is just a collection of point masses. So the rotational inertia of a hoop is also mr squared. We talked about that yesterday, but it's okay. Okay, please do this problem now. Good luck. I'll give you like a minute. And then I got to do one more problem with you. What the heck? Thank you. There's- At once? At once. Oh my God. Alrighty, hey, let's go for it. Initially, I hope all you've got is this 140 kilogram meter squared of the carousel multiplied by the 4 radians per second. That's all you got initially. That's the initial angular momentum. Afterwards, they are now rotating together. So you're going to add that 140 kilogram meter squared to the rotational inertia of that guy, which is going to be 55 kilograms times 1.8 meters squared. And then that'll be multiplied by the angular velocity of the system. Tell me, in linear momentum land, what does this problem remind you of? Where you've got one thing in motion and one thing at rest, and now the two are joined together. What kind of problem did I give you that looked like that? What's that?
The lumberjack.
The big
Oh,
fish.
yeah, no, because they're both at rest at the beginning of the
The
lumberjack.
big fish.
Whereas here, one of them's in motion. What, Imani?
The big fish eating the little fish.
Well, no, because is the little fish in motion or is he at rest?
He's at rest.
Okay, good. So she's got it. The big fish eating the little fish. I was thinking more huggy sort of thing.
Oh, the ice
Yes.
skater.
Yeah, the ice skaters. The one ice skater in motion and then hugging the second ice skater who's at rest. That's what this is like. This is no different than that, except it's angular instead of linear. So I end up with this guy equaling. Here, let me just a second. 140 times 4 divided by 140 plus 55 times 1.8 squared. So did you guys get 1.76? Anyone get 1.76? Okay, good, many of you. Obviously, it's going to go slower because that guy just increased the rotational inertia. Are you ready for the last problem? And if the bell rings, I may have to hold you, but here we go. I mean, hold you, because I didn't mean to hold you like hug you. Even though ice skaters hug, it's a beautiful thing. Here's A and here's B. Okay, so I've got two objects, A and B, that are rotating on a shared spindle. A is rotating counterclockwise, B is rotating clockwise. The mass of A is equal to 1.2 kilograms. The radius of both of them is 0.8 meters. And the initial angular velocity of A is 4.0 radians per second counterclockwise. The mass of B is 2.0 kilograms. the initial angular velocity of B is 3.0 radians per second clockwise. As drawn. I wonder if anyone can guess what's going to happen next. Say it again, Earl.
You're gonna touch.
Yeah, they're going to touch. In fact, A falls on B. A is just going to go blop and fall on B. So now they're going to be rotating together. Please find the final angular velocity of the A-B combination. And this is, by the way, this is like problem number 57. Okay, good luck. Please do this. I'll give you a minute, then I'm going to have to do it. I do want everyone to start with this, though. Initial angular momentum equals final angular momentum, because there's no external torques. Start with that equation and then go ahead and plug in. And if you're not remembering, remember the rotational inertia of a disk is 1/2 mr squared. So you'll be using that. Oh, I forgot the 1/2. Oh my God. Well, guys, I'm so sorry I'm out of time, but what did you do about these two guys on the left side? What's that? Yeah, subtract them. One guy's positive, the other's negative, you know, because of right-hand rule, this omega here is positive, and this omega here is negative, so I subtracted that guy. Which problem is this one similar to from linear land, by the way? What's that? Yeah, momentum, but which momentum problem? Which scenario is this like? Yes?
Ice skaters crashing into.
Yeah, the ice skaters crashing into each other now, yeah, because they have oppositely directed momentums and then they hug. Yeah, and that's what's happening here. And what'd you guys get? Well, here, I'll just do that. Sorry if the bell rings. What have I got here? 0.6 times 0.8 squared times 4 minus 0.8 squared times 3. So I got negative 0.384 equals, when you add up these guys, you get 1.024 omega f. So I ended up with negative 0.375 radians per second. Just out of curiosity, did anyone get negative 3.375? Okay, 2 of you, great. 3, that means I totally taught it to you guys perfectly. But are you okay with this idea? That's just the sum of the momentums equals the final momentum. And one more thing, is this rotating clockwise or counterclockwise?
Clockwise.
How do you know?
Because it's negative.
Yeah, because it's negative. We defined clockwise as negative, so this is rotating clockwise. Yeah. All right. Hey, good luck on tonight's homework. You're going to get a lot of problems like this coming.